InfluxData. And what I want to do is start with a little bit giving you a glance of where we are as a company, what we are building, what traction we are seeing, and comparing what's so special about time series, and then getting into the details as we go on, right? So to start with, we were founded, Influx was founded in 2013. It's based in San Francisco, 38 Go developers working for the company. So we are very big on Go as a technology. The mission of the product was to make it absurdly easy for developers to instrument everything. This is a paradigm shift in terms of like how a lot of solutions are in the big data space are emerging, where the initial approach was throw data and then ask questions. But more and more in the developer community, we are seeing a tendency to instrument applications from the get-go, instrument web pages from the get-go. So you don't have to deal with log parsing, you don't have to deal with sifting through a lot of unstructured data. You can start creating metrics, which is really what you care at the end of the day, from day one, right? And the focus is, again, for the product is based on the growing need for time series event collection. And that being said, it's not just a regular time series. We do deal with irregular time series data as well. And a lot of this growth is being funneled through technologies like containers, where a lot of data is short-lived, and you need ephemeral support of data. You need IoT support. And if you look at the IoT space, 90% of the data is all time series, because these are devices emitting events, maybe on a irregular basis or in bulks, right? But at the end of the day, all you want to do is essentially trend them over a period of time and use all kind of analytics behind the scenes. And from a differentiation perspective, as the platform has evolved, we have a lot of X's in the terms of, how better we can do in terms of performance versus various other platforms which were not built from the ground up as time series databases. And one of these comparisons is today's benchmarking exercise, which Robert will go deeper into. But the whole idea of the product was to get the fastest time to value. If you compare that with an OpenTSDB in the Hadoop land, it might take you days, weeks to really get started and get value from the data. Whether with Influx systems, we are trying to get that cycle time down to minutes and help keep the developer happy. There are almost too many tools for operations. There are, not that many for developers and DevOps guys. Just community traction, we have about 28,000 unique deployments and a lot of large enterprise customers. So what is time series, what and why, right? So there are different skill levels in the company. I'll speed this through this stuff. So what is time series data? It's essentially the way data is organized specific to capturing measurements, discrete events, summarization, aggregation. And there are a lot of time series functions that you need from a time series database. Means, maxes, counts, standard deviations, spreads, and things like that. Those cannot be served by general purpose databases. Those are very, very time specific functions which only a time series database can deliver. Now, why is this time series data so different, right? The workloads are different, right? You are dealing with values and points per second, and these are not necessarily objects, right? Like JSON blobs. If you're comparing that to a MongoDB or a JSON document to store object, is completely different versus what you are ingesting. You're ingesting metrics, and your system is optimized for metrics. The design, when you talk about the underlying storage engine design, earlier storage engines used were LSM based or log structured merge tree based. And we actually had to create a time structured merge tree specific storage engine, which was designed to keep the IO levels extremely low and only dealing with time series specific data. But why does it matter, right? Why do you care? Yeah, Influx did it, but why do you care? The whole idea is the instrumentation imperative is on, right? Developers are instrumenting everything from the get-go, right? Be it bots, be it APIs, be it containers, be it microservices, apps, you name it, right? Those days of throwing data and coming back and asking questions is gone. Um, there is an increasing requirement to act in real time or near real time, right? So if you are running bad jobs, well, you are about 5 years late to the game. The whole idea here is, there are streaming requirements. Businesses want to act on metrics in real time. Even if I was a marketeer and I wanted to just capture user experience on my website and take real time actions right there, right then, and maybe I'm sifting through millions and millions of data points at the same time and I want to launch targeted campaigns. If that data is not fresh anymore, even if it's delayed by a few minutes, that data is no good for me, right? So I want to analyze the data. I want to alert on that data. I want to even get into applying predictive models. For time series, it becomes very easy because it's all based on mathematics, right? There are so many mathematical models based on time correlation, right? And we see this segment of the market will grow exponentially with the advent of containers, microservices, sensors, and primarily IoT, right? So here's a super layman type example of a time series data. On the left, what you are seeing is traditional system metrics measured over time. As long as one of your axis is time, here you're looking at disk, CPU, memory, whatnot, right? On the other side, if you look at a business metric like financial data collection, and by the way, this is a real customer, right? Dow Jones, New York Stocks Exchange does actually use InfluxDB for a lot of these trading information, right? So you are wanting to trend over time, measure over time, predict over time, right? What is not an example of time series data? Hey, if I were trying to find out my social media impact, where am I, my interconnections, right? It's not very good at plotting relationships between data, right? If you're trying to find out, hey, on the right side, there is an athletic effectiveness graph of a classroom, and for different grades. And these are like every student is rated on how athletic he is. That's not time series data, right? These kind of data sets are very important. That's one segment of the market, but that is not time series data. That is absolutely not what we do. Just to reaffirm, right? On the left side, if you're looking at social media impact, and if you were tagging royal baby hashtag usage hour on hour, or maybe every minute, or maybe every second, right? That's time series data. However, if you wanted to see the same tweets by population across every country by demography, that is not time series data on the right side, right? So just to set the context right. So for this bake off, there are two platforms, right? And we will be doing a similar comparison. A lot of existing vendors in different spaces have now started entering time series, right? They have started blogging about it. They have started putting offerings around time series, but most of these platforms were not designed from the ground up as time series, right? So if you look at some of the history of InfluxDB and Elasticsearch, right? Open source projects. Uh, Elastic was built on Apache Lucene, and obviously they started 3 years before us, um, and the versions. They have a lot more traction because they have a number of years on us in terms of history. But we are growing at a much faster clip. Operating system wise, you can see it runs both on Linux, and for us, we chose Go as our primary language just from the sheer performance perspectives of it, right? And there are so many Golang talks. So why Google chose Go as the main computing platform? It was traditionally to deal with or gain the benefits of I/O and the resources that are available on any system, right? As well as the cross code compatibility. This is not a Go talk. What I'll do is I'll hand it over to Robert and help you guys walk through a deep dive view of what the benchmarking was. But with this history, maybe you can appreciate it a little better what we ended up doing.
All right, so before we jump into the actual methodology behind the benchmark, which is the bulk of the presentation, we wanted to quickly review the benchmarks themselves, at least the results, so we can kind of work our way backwards, so to speak, on how we came to these results. So the first thing that we want to understand is what were the versions that were tested. That's going to be InfluxDB version 0.13, as well as the latest version from Elastic, which would be, at the time of testing, 5.0.0 Alpha 1. A little bit about the benchmarks themselves. There's basically three main things that were benchmarked. The first one was the data ingest performance. So this is going to be measured in values per second. The second one was the on-disk storage requirements, and this was measured in megabytes. And then lastly, the mean query response time, which was measured in milliseconds. A little bit about the data set itself. We went with the scenario of a common DevOps monitoring and metrics use case because traditionally when folks come to us and they're weighing using Elasticsearch or InfluxDB, it is inevitably for some sort of a monitoring or metrics use case. So we felt that it would be the use case that would be of most apropos, but also of most value for people that are considering either technology. So we're measuring 100 values across 9 subsystems. So here we were measuring CPU, memory, disk I/O, kernel, network, as well as Redis, Postgres, and Nginx. The number of servers in the data set was 100. The values that were measured per server was 100. The measurement interval was every 10 seconds, and the data set durations were 1 day, 2 days, 72 hours, and 96 hours, which gives you a total value in the data set per day of well north of 86 million, it looks like there. So what did the graphics look like? So on our first benchmark, where we were looking at data ingestion, higher is better, obviously, in the graph. Influx came out at 8x better than Elastic. And when it came to storage requirements, in this case, we're talking about compression. InfluxDB had a 4x to 15x better compression for the data that you needed to store on disk. And then finally, the third portion of the benchmark, which was the query performance, InfluxDB yielded at least 3.5 better query performance than Elastic. So all of these graphics, as well as detailed explanations about what went into the benchmarks and how things were measured, you can either check that information out on the blog post that came out as a supplement to this webinar, but you can also download the technical white paper if you want to get deep into the details. And of course, if you really want to go deep and want to look at the actual code behind the benchmark, we encourage you to check out the GitHub repository. And Robert's going to talk about all this stuff in his presentation. So let's jump into his portion of the presentation now.
Okay, thanks for that excellent intro, Shubhra, and thanks for coordinating the webinar, Jimmy. I'm a little bit less practiced than the other folks on the panel at the webinar here, but I'm going to try to give you an in-depth look at not just what the benchmarks are that we ran against Elasticsearch, but kind of why, and sort of why is now a good time. You can find our results online. There's a white paper, there's an open source GitHub project. So this talk, which we also will be making available afterwards, is going to run you through the rationale. And over the last 2 months, we've been building a benchmark system to rigorously compare Influx versus other data stores, and Elasticsearch is the first one. So the big question we were trying to ask and then answer is, for workloads you actually care about, is InfluxDB faster than Elasticsearch? It's true that Elasticsearch is a very good piece of software. It's used successfully in huge numbers of use cases in many different setups. But as Shubhra mentioned, Influx is specialized for time series data, and we want to kind of show that off. And we have a number of goals that sort of framed the benchmarking project. The first one is we wanted to be realistic, going back to the workloads that you care about. So there are a lot of benchmarks that are synthetic, and they're also kind of really most interesting for people who like databases. I like databases, so I can think of a bunch off the top of my head, but those don't necessarily map that easily to real world use cases. So for example, if I have some benchmark that shows how the number of mutual exclusion locks, how many of those suffer contention as you increase the write load, for example, I find that very interesting. But it's very hard for our customers to connect that to, how will that work for me? So we took a different approach. We decided to make it as close to the real thing as possible. And so we call that use case oriented benchmarking. And right now we have support for one use case, and that's developer operations or DevOps. In the future, we'll be looking at IoT and sensor data, as well as geographic data. Well, that's on the roadmap anyway. Our second goal was we wanted to be rigorous. So these are complicated systems, especially general purpose ones like Elasticsearch. We wanted to design this benchmarking suite end to end so that we could be sure that we were doing a good job with both data systems. And that means we wanted it to be correct semantically within each database. And we also wanted the responses that come back from each database to be identical. And we did a lot of work to make that possible, and I'll come back to that in a few slides. Of course, like any good scientific study, it should be easy to reproduce what we did. I think that's par for the course these days. Our code is open source, it's MIT licensed, and here's a link that you can use to find the source code to our benchmarking suite. And a big one is we wanted to be fair. So there's always a mixture of incentives and intentions behind any kind of commercial software. And so one of the reasons that I was brought in as an external contributor is to try to show Elasticsearch in the best light. So one thing that we did is we learned from Elasticsearch experts how to get the best performance. We explored a number of different index templates, which are how you create sort of automatic schemas, if you will, inside of Elasticsearch. We dug into how Lucene actually stores data inside of the column indexes. So one of the reasons Elasticsearch is so fast for many workloads is that it uses Lucene under the hood, which is a very good project. We learned how to tweak Elasticsearch to increase bulk write throughput. And in fact, we use the official recommendations from Elastic, the company, for setting up time series data storage. So onto the methodology, now that I've outlined the goals. We have 5 phases, and you can think of this as both conceptual and also how to use the tools. Each one of these corresponds to at least one program. The first phase is how do we generate data? So in general, we're going to be creating a data set, loading that data set into our database of choice and taking measurements. We're going to be creating a query set, which will know about that data and query it, kind of make read operations, aggregation operations. And then the fourth phase will measure those actually being run. And then the final phase is we'll validate the results and make sure that they're correct. So the DevOps data generator creates time series points that correspond to server telemetry. And the idea here is that DevOps being a use case, it models and it simulates what maybe a system administrator would be seeing in production if they have maybe a data center full of computers or a big bunch of VMs on AWS. And the program name for this part is called bulk data gen, and it's a simple Go binary. So the data is generated deterministically, and this is one of the things that goes back to the reproducible and the rigorous goals. We generate a lot of random numbers, but those all originate using a pseudo-random number generator, which by seeding it with values at the beginning of any simulation run, we can use that to create data that when we make it, it's identical in its parameters for Elasticsearch and for Influx. And so if you have, say, 100 hosts, the tags and the values that get emitted as bulk data to be written or as query parameters to be read, used in the query submitter, they'll be identical. And so this was a big part of our design. So getting more concrete about the DevOps use case data generator, going back to what Shubhra said, we have measurements. So here are 9 measurements that we simulate for each server. Again, this is like a server fleet. So maybe they're running a bunch of software. We want to keep in touch with how what's the memory pressure like, how much available CPU is there, and also on the application layer, maybe some statistics from Nginx or Postgres or Redis. So these are 9 different measurements that would be coming from a single virtual machine or server, and they'll be coming at us every 10 seconds. And within each one of these is approximately 12 to 20 fields that all have numeric values, and I'll get into those in a second. So the second part of a generated point in time after the measurement name is what we call tags. And so these are initialized once at the beginning of a simulation. We assign them to these simulated hosts. So the idea is that you may, in reality, you would have tags for which data center is this computer and which rack is it in. And then the administrator could slice and dice the data by those tag values and understand more what's happening in her data center. And we try to be pretty realistic with this. We use real AWS region and data center names, and for the rest of them, we made up a small set of arbitrary values. So getting more concrete with the fields and the values they hold, this is an example from the CPU measurement, which will be coming out of every machine every 10 seconds. So far we have the measurement name, CPU, we have the tags, which are the same for every host machine, and then we have these values. And so we actually put a lot of effort into making these reasonable and sort of realistic. In particular, a lot of the values that we generate are what I call a clamped random walk, where you have a minimum value and a maximum value. And then within that, there's one state, and it actually will kind of randomly walk up and down through time. And this is much more realistic than, say, picking a number uniformly at random, because there are correlations through time about how resources get used. This also lets us be realistic in terms of the compression that you would see in a production system. So because values are correlated through time, databases that are aware of those properties of being correlated through time, they can utilize compression. And for example, Influx uses some pretty advanced delta compression, among other things, to save disk space. And then finally, the fourth part of any data point is the timestamp. Here I gave an example. It's based on the beginning of the Unix time epoch, and Influx has nanosecond precision. Elasticsearch has millisecond precision, which is good for many workloads. As Shubra mentioned, there are a lot of use cases where nanosecond precision is desirable. And just to reiterate, the timestamps kind of proceed in lockstep in 10-second intervals. So here's an example to be concrete, and I split it up into multiple lines for formatting, but this would all be one line in the Influx bulk line protocol format. So the first part is the measurement name here at CPU. The second part is the machine-specific tag set, and this is shared amongst all the points for a single machine, and it's different between machines. So you can see here that we create a host name, we call it host 0, we pick a region, we pick a data center, and so on. And finally, the most interesting part, I think, is the fields. These are generally percentages because it's a CPU measurement. So they're all between 0 and 100. And if I were to graph this for you, you would see it sort of running up and down sort of randomly, kind of like the stock market example you saw earlier. And that's because it's, again, correlated through time to mimic what you would see in production. And then finally, the nanosecond precision timestamp. For Elasticsearch, we, of course, did the formatting differently. It's rendered to a file in the bulk write format that Elasticsearch expects. That recaps what I was just saying. But right now we support 2 different formats, and that's the bulk write format of Elasticsearch and the bulk write format of Influx. So one thing that we took great care to do is to, again, this goes back to being fair and rigorous, is data serialization is not free. So when we're running these simulations, calculating the random walk values and so on, that part is really simple for our computers. But to actually write the data to a file in a way that's ready to be submitted to the database, that encoding process not only takes time, but it's different between the databases. So Influx has a very straightforward line protocol that's space and comma separated. Elastics is a little bit more complicated in that it's line delimited JSON documents. So Go's JSON serializer makes a lot of heap allocations. It uses reflection. And so in the end, Go's JSON serialization makes writing the Elasticsearch data slower. But that's okay because we do this in phases. So the first phase is we generate the data and we save it, and it's all pre-serialized. And then in the second phase, we use that data to query. Making it concrete, for the report that we published so far, we created what we call the DevOps 100 dataset. So this simulates 100 hosts over various time periods throughout the course of about a week. So that was a lot of information on the simulation and data generation phase. But in summary, we create data based on a realistic simulation of servers. Every 10 seconds, each simulated host emits 100 different numeric values, and those are spread across 9 measurement points. And we save that to a gzip compressed file. Second phase is we are going to use that generated data and benchmark bulk writes. So this is written in kind of a standard Unix style where we accept a file input coming in from standard in. And because for each of these data stores, the bulk write format is line oriented, we can share some logic there. So the way it works for Elasticsearch is that we read 2 lines in, that represents a point in their protocol. The way it works for Influx is we read 1 line in, that represents a point in Influx's protocol. The bulk loader has a parameter for the batch size, and for our benchmarks, we used 5,000. And so what happens is, say for Influx, the bulk loader will read in 5,000 lines from standard in, and then create that or move that into a batch, and then submit that in a different Go routine to the to the Influx endpoint. For Elasticsearch, same thing, but it's 2 lines at a time. So in our case, 5,000 times 2 gives 10,000 lines per batch. Then when we submit that to the Elasticsearch endpoint, the format of these 2 databases, of what they accept for bulk writes, it's actually pretty simple. As we add more data stores to the benchmarking suite, these programs will necessarily become more complicated. One of the main axes that we changed or measured when doing the benchmarking is how many parallel workers to use to submit bulk writes to each database. Yes, and between the 2, you really get to change the parallelism factor and how big the batch size is. So the first we're going to look at in detail is the Elasticsearch bulk API. So going back to this notion that we had to really dig into Elasticsearch to understand how it worked and how to set it up best for time series data and how to make it a fair comparison with Influx. One thing that we saw a lot is that there's confusion about which index template sort of setup to use to store and analyze time series data on Elasticsearch. And there's enough of a schism that we actually support 2 different index templates. And they sort of represent 2 different points on a continuum of complexity and use case specialization. So the first one is what we call the default template. It's very close to an empty index template. And what that, in Elastic, as an aside, you store data about keywords, strings, but you also store effectively blob data. And these are called the source and the all fields, and they're used in different ways for the main use case of Elasticsearch, which is document search and retrieval. So the default template includes a lot of that data. However, in the time series use case, it's never really used query time. It's only used to return verbatim copies of in our case, time points, which is not very useful for aggregation queries. But again, this is very straightforward, and it's what a sort of an uncomplicated user of Elasticsearch might try to do. Moving on from that, and this is closer to what Elastic, the company, recommends users do for time series data, is implement what we call the aggregation template. So it throws away those so-called blob fields that are mainly optimized for doing document retrieval and search, and it starts to specialize Elastic to the time series use case. And in particular, you noticed that before the data generator had 4 sections per point, and that's the measurement name, the tag set, the fields, and the timestamp. Well, it turns out in Elastic, the tags and the fields are about the same. The only difference is that the tags have values that are strings, and we want to do kind of filtering based on those, whereas the fields are numeric. So tags are something that we don't care about aggregating over tags. That doesn't even make sense. So in the aggregation template, we do what's called, we make those a keyword, which is a special type in Elastic. And then for fields, we we discard a lot of the source data and just keep the numeric values around. So during our testing, Elasticsearch 5 Alpha was released, and so we made an effort to make these schemas work with both Elasticsearch 2.3 and Elasticsearch 5 Alpha. And they seem to be releasing new alpha versions fairly regularly, so we hope to get to the official ES5 release soon and have results for you. Of course, like I said, this is open and we're trying to be fair, so please let us know what you think about how we did the Elasticsearch bulk loading. The source code, again, is in the repository, and yeah, we're trying to be very open with the community about this. So excitingly for me as the implementer, Influx required no database-specific configuration. So here's an example output from the bulk writer. Again, it takes line-oriented data from standard in and submits it possibly in parallel to either an Elasticsearch endpoint or an Influx endpoint. And so here we can see we loaded about 4 million items in about 40 seconds with 16 workers. This happens to be with Influx, and it gives you an average rate. And here it's about 100,000 lines per second. And if you do the multiplication of how many sort of separate numeric values are in each line, that adds up to be a much greater number that's actually closer to Shubra's 500,000 per second number. So now we enter phase 3 of 5, where we generate queries. And again, this is sort of this, we generate, we save, and then we use that saved data to create a benchmark. So we're going to create ready-to-use queries and save them to a file. And here, sort of similar to the simulator that generated the data that we loaded into the database, the query generator logic is also shared between the databases. I want to make an aside to talk about serialization again. In this time, it's even more important. So many benchmark suites generate query parameters and then serialize those into the wire format at the same time as running the benchmarks. And we don't, because that would be mistaken. So just getting back to sort of the differences between the databases, for example, Elasticsearch uses JSON pervasively. Influx has a simpler sort of query language. And if we were to do these serialization operations inline, then it would very unfairly penalize Elasticsearch. In general, the way we think about queries is that we have sort of a concept of a query first, and that's maybe a query template. And within each query template, which represents an operation that somebody would want to use that's relevant to the use case. So for example, maybe an administrator would like to visualize the CPU usage across some number of hosts. Well, the variables in there are the number of hosts or which ones, the host names, and then the time frame and maybe the bucketing interval. And so we have a query template, and then we put values into it. And the values that we put into it are determined through a pseudo-random number generator, similar to the simulation logic as before. And we have a seed, and again, it's all entirely deterministic and reproducible. So here are some example query types. What's the max CPU usage over 4 random hosts where there's a specification of where host name equals A, host name equals B, and so on, during some hour, and we want to have that grouped by minute intervals, or the average CPU usage over the whole server fleet during some day, grouped by hour and grouped by host name. And we're continually iterating on the queries, so there will definitely be more to come. To make it concrete, here's an example of a query template for Elasticsearch. So again, it uses JSON, so you can see here that we had to, as an aside, one thing that we really had to understand was the query language of Elasticsearch. So because you can do almost anything with Elasticsearch, it can be rather tricky to construct the queries that you really want. But here's an example. So this is straight from the Go code in the repository. You can see here that most of these are string literals, but some of them have template wildcards, and this is in the Go text to template format. So timestamp here takes a greater than or equal start time. So you can imagine that as a timestamp that's greater than or equal to start timestamp. And same thing with the less than, so it creates a window. Moving down, the interval bucket, that will usually look like hour, minute, day. And then getting a little bit lower for this query type, we're actually taking an average of a field that is a parameter. And then making it concrete, this is the same query template, but with some of the parameters filled in with various data. The timestamps, you can see here the greater than and less than. Those actually form looks like a day. And you can see by the number of hours and minutes and seconds, 19, 24, 45, that actually came from our random number generator. And then at the bottom, the field is usage user, and just above that, the bucketing interval for this is 1 hour. Here is the equivalent query in InfluxQL, which is Influx's SQL-like query language. So I personally find this easier to read, and one of the reasons that's true is because Influx is designed for the use case of working with time series data. And so whereas Elasticsearch has a general purpose query language, InfluxQL is statically typed and special purpose. And so this template says the same thing as the previous slide. Select the average CPU usage. It's called usage user here. Where time is between these two timestamps, grouped by the hour and the host name. So at the end of the query generator, we store them in a file of job. I've actually never said that out loud. It's the Go binary serialization format. And that is sort of a Go native way to encode objects. And right now we can deserialize this file of queries at about 700,000 requests per second. And that's fairly fast for a single node. We've hit no limits yet. But when we get to benchmarking clusters, we have some plans for how to make this faster. So it's very important when you're making benchmarking software that the program that is conducting the benchmark can go faster than the program that's sort of receiving the benchmark or the thing being measured. As I mentioned a few times already, we use a deterministic random number generator to fill in values for these queries. And so with the right seed and the right timestamp interval for a command line parameter, these are 100% reproducible. And a small number of statistics are printed after the end of the query generation. So here we can see doing an influx query set, it picked a random seed for us, and then it serialized 10,000 queries that are about those points. And same thing here for Elasticsearch. Yeah, we've been iterating on the query types as we get closer to this use case centered design. So there will be some churn, but you're welcome to go look at the source code. That's the URL for it. So phase 4 of 5, this is probably the the one that most people think of when they think of benchmarks, but it took a lot of work to get up to this point. So we're going to be looking at benchmarking read queries. So to catch you up to this point, we have a file of compressed serialized queries that are in a database-specific format, but they have not yet been submitted to the database for measurement. And now we're going to do this. So right now, there's one query benchmarker program, and that's because both Elasticsearch and Influx accept queries over HTTP. So these serialized queries have, of course, different parameters inside of them, but they are HTTP requests. And the common parameters that you can alter are how many requests to make in parallel and what's the destination URL of the machine. The query benchmarker is on purpose fairly dumb, and that's to keep most of the logic outside of the hot path of actually running the benchmarks. So just again, we have the data generator, which is complicated. We have the data loader, which is simple. We have the query generator, which is complicated, and we have the query benchmarker, which is simple. And when we run it, finally, after all this work, we see some example output. So this is from a version about 2 weeks ago. We, at that time, had a number of different query templates. And so these were all being run one after the other against an Influx instance that had been loaded with one of the DevOps 100 data sets. And you can see that we ran 5,000 queries with parallelism factor of 4. And these are broken down by query type. And so these are all the same, except that they have a where clause that specifies different numbers of hosts. So you can see it goes in powers of 2 from 1 to 32. And the idea here is if we can sort of see how the latency scales as you make more you spread your fingers wider when you're collecting this data. And right here you can see that Influx, in my opinion, scales fairly well. And at the end, because these latency numbers, when you have parallelism, you need to take into account what was happening at the same time as the other ones. We return the total wall clock time. And then finally, we validate results. And this is going to get us our rigorous and correct goal. And let me explain that real quick. So we really care about correctness because, as we all know, writing software is hard. And working with just one database, especially a general purpose one like Elasticsearch, can be a little error prone. You have to really know what you're doing. And so for the benchmarking suite, we're working with multiple databases and writing software for all these things. And so I wanted to find a way to sort of prove to myself that the whole thing was correct. And in particular, there are 4 questions that kind of breaks down into. Were the parameters and the points identical for both databases? So was the data generator correct? Was it reproducible, deterministic? Were the points loaded correctly? Did they all get in the database? And then for the query generation, were the parameters identical for both databases? So although the formats are different, as you saw, definitely the timestamps, for example, in the same query should be the same. And then finally, and this is more a case for Elasticsearch and Influx, but we wanted to make sure that the queries we were making were actually returning the results that we expected. So the validation step checks that the numerical results from queries are identical. So here we're going to show how it's done. Right now, it's a manual process. We're looking at ways to automate this. So these are responses from Elasticsearch and from Influx. And what happened here is that we took a data set with the same parameters, but in different database formats, loaded that data set, and then we ran a query set in the 2 different formats against each database. And so this is the same query. I think it's query ID 0. And this is the first box here is the response that came back from Elasticsearch, and the second box is the response that came back from Influx. And so what we're looking to see here is that, given the different bucketing intervals, the time intervals, the fields, the where clauses, are the values the same? And you can see here that the keys that come back are, so first of all, you can see it says it's the January 1st, 2016 at midnight, and then the second one for Elasticsearch is the same one, but at 1 a.m., and you can tell that the same is for Influx as well. The timestamps match up exactly. And then the second part, which is personally what is most exciting to me, is that the calculated aggregation values are extremely close. In this case, they're almost identical. So you can see here that it calculated an average of the given field over that hour, and the value it came up with in Elasticsearch is 16.666385. And if you look at Influx, it's exactly the same. And if you look at Elastic for the second field, 31.869 ... And if you go down to Influx, the first digit that I see that's different is past the 10th place. So this to me sort of proves, empirically at least, that our simulation approach worked, and our our whole suite is rigorous and correct. Of course, like I said, there are small floating point differences. That's to be expected. And like I said, it's manual right now, and we're in the process of automating it. So thanks for sticking with me this far. Let me wrap up. So did we meet our goals? We wanted to be realistic. To do that, we modeled our data and our queries on a real-world use case that we learned about from our customers. And by using a simulation approach, we did our best to sort of come up with realistic numbers, in particular using random walks for many of the values. Were we rigorous? Well, the query validation approach shows that we have some certainty that we are correct in what we've done through and through. Is it reproducible? Absolutely. Given the same random number generator seed and other configuration parameters of the generators, we have completely deterministic data and query generation. And it's absolutely open. All the code is available on GitHub, where it's under an MIT license, and I will be reviewing issues and pull requests as they come in. And were we fair? We made a great effort to accommodate Elasticsearch. We learned how to configure it. We learned how to do JVM tweaking, at least tweaks that are standard for Elasticsearch deployments. Different index templates. We learned about Lucene. So we really tried to give Elasticsearch a fair shake. Thank you very much.